chemical bonding, electronegativity, and determining bond polarity. In this tutorial, we will be looking at electronegativity defined, determining bond polarity, nonpolar covalent bonds, polar covalent bonds, and some worked examples at the end. Electronegativity. Electronegativity is the ability of an atom in a molecule to attract electrons to itself in a chemical bond. The electronegativity values range on a theoretical scale from 0.7 cesium to 4.0 fluorine and are unitless. The greater an atom's electronegativity value, the greater the atom's ability to attract electrons to itself in a chemical bond. Remember, ionization energy measures how strongly an atom holds on to its electrons. Electron affinity is a measure of how strongly an atom attracts additional electrons. You do not need to memorize electronegativity values. However, you should understand the periodic trends, allowing you to predict which of two elements is more electronegative. Bond polarity. Bond polarity describes how bonding electrons are shared between atoms that form a covalent bond. Nonpolar covalent bonds. A covalent bond in which the electrons are shared equally by two atoms. There is no electronegativity difference in the covalent bond. So for an example, a Lewis structure of a chlorine molecule. Each of these chlorines has an electronegativity of 3.2, and if we take the difference between these two, it is 0. We see the same trend in bond polarity in diatomics when we look at an oxygen molecule where the difference of 3.4 minus 3.4 is 0, and also in a nitrogen molecule where 3 minus 3 is also 0. Polar covalent bond. A polar covalent bond is a covalent bond characterized by unequal sharing of bonding electrons between two atoms. One of the atoms making up the covalent bond exerts a greater attraction for the bonding electrons than the other atom due to a difference in electronegativity values. So if we watch this video from this PhET simulation, we can see at the beginning that atom A electronegativity is less, and so is the atom B electronegativity. So therefore, the bond character is classified as more covalent at an equal distribution of the shared pair of electrons between A and B. But as we start to move the slider on atom B across and make atom B more electronegative, we can see that there is an unequal distribution in electrons as the electrons get pulled closer to B. If we switch over to electron density, we can see that the electrons are pulled closer to B and away from A, giving B a slightly negative charge and A a slightly positive charge. The greater the electronegativity difference, the more polar the bond. In other words, the greater the ionic character of the bond. The shared electron pair is pulled closer to the higher electronegativity atom, resulting in a polarized bond, otherwise known as a dipole. The atom with the greater electronegativity gains a partial negative charge, represented as a lowercase sigma with a negative after it. The atom with the lesser electronegativity gains a partial positive charge, represented again by a lowercase sigma with a positive charge associated with it. A bond polarity arrow is drawn above the covalent bond in the Lewis structure from the atom with the lesser electronegativity value to the atom with the greater electronegativity value. So in this case, hydrogen has an electronegativity of 2.2, while chlorine has an electronegativity of 3.2. So the polarity arrow would be drawn from the hydrogen to the chlorine. A slightly negative charge would be drawn by the chlorine, and a slightly positive charge would be drawn by the hydrogen. An electron cloud can be used to show the probability distribution of electron density in a molecule. So the hydrogen has less electron density and the chlorine has a higher electron density around it, again symbolized by the sigma with a negative charge and the sigma with a positive charge. Let's look at an example. Lewis structure for a hydrogen fluoride molecule. In this scenario, we'll have a hydrogen with one valence electron, giving us a total of 1 electron from the hydrogen. The fluorine, also 1, has a total of 7 valence electrons, 7 electrons to work with here. If we add them together, we'll get a total of 8 valence electrons, or the equivalent to 4 electron pairs. So we'll draw the fluorine and the hydrogen, and we'll connect them together with one shared pair. That leaves 3 electron pairs to work with. We'll use those 3 electron pairs as non-bonding pairs around the fluorine. 1, 2, 3. Then we'll assign electronegativity values, with hydrogen being 2.2, fluorine being 4. The polarity arrow will go from the hydrogen to the fluorine, showing that the bond is polar. We can see this again in the electron cloud diagram, with the hydrogen getting a slightly positive charge and the fluorine having a slightly negative charge. Let's look at another example, looking at dihydromonoxide, more commonly known as water. In water, we'll have 2 hydrogens with 1 valence electron apiece for a total of 2 electrons, 1 oxygen, 6 valence electrons for a total of 6 electrons. Add those together, we'll have a total number of electrons equaling 8, or the equivalent to 4 electron pairs. We'll start out with an oxygen, 2 hydrogens, and shared pairs drawn between the 2. That's 2 shared pairs out of our 4 electron pairs, leaving 2 non-bonding pairs. 1 non-bonding pair at the top, 1 non-bonding pair at the side. Then we'll assign electronegativity values, with hydrogen being 2.2, the other hydrogen being 2.2, and the oxygen being 3.4. Now we'll put in our polarity arrows, going from the less electronegative to the more electronegative. This shows that the bonds are polar and that the electron density will be closer towards the oxygen. This again can be represented in an electron density model, with the oxygen being slightly negative and the hydrogens being slightly positive. So what did you learn in this tutorial? We looked over the definition of electronegativity. We talked about how to determine bond polarity. We talked about nonpolar covalent bonds, polar covalent bonds, and then did some worked examples at the end. Need more help? Feel free to contact me. Have a great day.